Hello, this is Professor Uma, Department of Mathematics, Hindustan College of Engineering and Technology, Coimbatore. Today, we'll be discussing about how to find out the complex integration using residues theorem. First of all, let us see what are residues and then we'll see how to evaluate the residues. As a part of residue, if A is an isolated singularity of any type for the function f of z, then the coefficient 1 by z minus a in the Lorentz expansion of f of z at z equal to a is called the residue of f of z at z equal to a. The region for this is 0 less than modulus of z minus a less than r. How to find out that residues? Let us see the formulas. If z equal to a is a simple pole of f of z, then the residue of f of z at z equal to a is limit z tending to a of z minus a into f of z. Suppose if z equal to a is a simple pole of a function f of z which is of the form p of z by q of z, then the residue is limit z tending to a of p of z divided by q of z. And as a third case, if z is a pole of order m, then how to find out the residues means this is the formula. Residue of f of z at z equal to a, where a is a pole of order m, is 1 by m minus 1 factorial into limit z tending to a of m minus 1th derivative of z minus a the whole power m f of z. Here comes residue theorem, Cauchys residue theorem. Its statement is, if f of z is analytic on and inside a simple closed curve C, except for a finite number of singularities, say a1, a2, etc. up to an, they are lying inside C. And if capital R1, R2, etc. up to Rn are the residues of f of z at these singularities respectively, then we can calculate integral over C f of z dz equal to 2 pi I into R1 plus R2 plus etc. up to Rn. That is sum of the residues. Here comes an example for that. Evaluate integral over C z minus 1 by z plus 1 the whole square into z minus 2, where C is the circle modulus of z minus I equal to 2. How to find out the evaluation? We'll see by using Cauchys residue theorem. Yes, the given function f of z is z minus 1 by z plus 1 the whole square into z plus 2. First step is we have to find out the poles and also the order of the pole. So the first factor is z plus 1 the whole square. So if it is a factor z plus 1 the whole square, then z equal to minus 1 is a pole of order 2. Next factor is z plus 2. So z equal to minus 2 is a pole and it is of order 1. So it is a simple pole. So we have to calculate whether these 2 poles are lying inside that modulus of z minus I equal to 2. So that should be our next step. Yes, we'll substitute z equal to minus 1 in modulus of z minus I equal to 2. We'll find that modulus of minus 1 minus I, which is root 2. Of course, this is less than 2. So, z equal to minus 1 lies inside C. Whereas, when you substitute z equal to minus 2 in modulus of z minus I equal to 2, we have modulus of minus 2 minus I, which is nothing but root 5. And we all know it is greater than 2, and hence z equal to minus 2 lies outside C. So it is enough to find out the residue for z equal to minus 1 alone. So we are trying to find out the residue of z equal to minus 1 using the formula. Of course, it is of order 2. So by formula, this is 1 by m minus 1. Here m is the order of the pole, which is 2 now. So 1 by 2 minus 1 factorial into limit z tending to minus 1 of m minus 1th derivative, that is 2 minus 1th derivative, that is first derivative. So first derivative of z plus 1 the whole square into f of z. Yes. So if you find out that f of z, if you substitute f of z as z minus 1 by z plus 1 the whole square into z plus 2, that z plus 1 the whole square is getting cancelled. So we have a term z minus 1 by z plus 2, that is to be differentiated once. Yes. So since we have to differentiate z minus 1 by z plus 2, we have to use u by v form. So u v dash minus v u dash by v square. Here v is z plus 2. So z plus 2 the whole square into the numerator is z plus 2 into 1 minus z minus 1 into z plus 2 differentiation is 1. So 1, which is equal to, on simplification, 3 by z plus 2 the whole square. So that is the differentiation of z minus 1 by z plus 2. Now we have to take the limit z is tending to minus 1. Yes, hence if you substitute z as minus 1, we have minus 1 plus 2 the whole square in the denominator, 3 in the numerator. So on simplification it becomes 3. Hence the residue of z equal to minus 1 of is 3. Hence by residue theorem, integral over c z minus 1 by z plus 1 the whole square into z plus 2 dz is 2 pi I into sum of the residues. Here only one residue, that value is 3. So 2 pi I into 3, which is 6 pi I. So that is the answer for the given integral. So that by using Cauchy's residue theorem, we are evaluating the value of the given analytic function. Thank you.